I'm super excited to start the very first lesson on big data. And thank you again for choosing this course. I promise we're going to learn a lot about Hadoop and big data. Ready? Let's get started. In this lesson, we're going to see what is big data and some examples of big data first. Then we'll see what are the problems that come with big data. We will then talk about what Hadoop can offer in terms of solutions to big data problems. And finally, we'll compare traditional solutions with Hadoop. If you ask me, tell me in one sentence what is big data, I would say big data is extremely huge volume of data. To that answer, the follow-up question you can ask is what is considered huge? 10 GB? 100 GB? Or 100 terabyte? What is huge? There is no straight hard number that defines huge or big data. I know this is not the answer you're looking for. I can see your disappointment. There are two reasons why there is no straightforward answer to this question. First, what is considered big or huge today in terms of data size or volume need not be considered as big a year from now. It is very much a moving target. Second, it's all relative. What you and I consider to be big may not be the case for companies like Google and Facebook. Hence, for those two reasons, it's very hard to put a number to define big data volume. Let's say if we are defining big data problem in terms of pure volume alone, then in our opinion, when you say 100 GB, I would say not a chance. It is not big data. We all have hard disk greater than 100 GB, so it's clearly not big data. How about 1 terabyte? Still no, because a well-defined traditional database can handle 1 terabyte or even more without any issues. But what about 100 terabytes? Likely, some would claim 100 terabytes to be a big data problem and others might disagree. Again, it's all relative. What about 1000 terabyte? Now we are talking in scales of petabytes. I would say it's definitely big data. You have to understand, volume of data is not the only factor to classify your data to be big data or not. So what are the factors should be considered? Let's say we work at a startup and we recently launched a very successful email service where users can log in to send and receive emails. Our email service is so good, let's say it's even better than Gmail. In 3 months, we have 100,000 active users signed up and using our service. Hypothetically, let's say we are currently using a traditional database to store email messages and its attachments. Also, our current size of the database is 1 terabyte. So, do we have a big data problem? The simple, straightforward answer is no, because 1 terabyte is not that huge to classify it as a big data problem. The more important question is, at this growth rate, will we have a big data problem in the near future? To answer that, we need to consider 3 factors. The first one is volume. It's an obvious factor, right? In 3 months, our startup has 100,000 active users and our volume is 1 terabyte. If we have positive growth at the same rate, at the end of the year, we will have 400,000 users and our volume will be 4 terabyte. End of year 2, with the same growth rate, we'll have 8 terabytes. What if we doubled or tripled our user base every 3 months? So the bottom line is, we should not just look at the volume when we think of big data. We should also look at the rate in which our data grows. In other words, we should watch the velocity or speed of our data growth. Velocity. This is the next important factor to consider. Velocity tells you how fast your data is growing. If your data volume stays at 1 terabyte for a year, all you need is a good database. But if your growth rate is 1 terabyte every week, then you have to think about a scalable big data solution. Most of the time, volume and velocity is all you need to decide whether you have a big data problem or not. The next factor to consider is variety. Variety adds one more dimension. Our data in traditional databases are highly structured, that is rows and columns. But take for instance our hypothetical startup email service. It receives data in various formats, right? text for the actual messages, images and videos as attachments. When you have data coming into our system in different formats and you have to process or analyze the data in different formats, traditional database systems are sure to fail. And when combined with high volume and velocity, you for sure have a big data problem. So whenever you're asking yourself whether I have a big data problem or not, take these three V's, volume, velocity, and variety, into consideration. This will guide you in understanding whether the problem you're facing now is a big data problem or not. This happens to big data consultants all the time. They will be called in by clients with data storage or performance issues and hope that a big data solution like Hadoop is going to solve their problem. And most of the time, their answers will fail in the volume and velocity tests. The volume will be in the higher gigabytes or low terabytes, and their growth rate is relatively low for the past 6 months and in the foreseeable future. Hence, their volume does not qualify as big data. And also their data growth will be very low and it fails the velocity test as well. What the client needs is to optimize the existing process and not a sophisticated big data solution. Now you know what is big data. And given a scenario, if someone comes up to you and asks whether their data problems can be solved by big data solutions, you know what are the factors to consider to make a sound decision. Volume, velocity, and variety. The three V's. Okay, so when we say big data, we are potentially talking about hundreds to thousands of terabytes. If you are new to big data space, you're probably wondering, is there really a use case? The answer is absolutely yes across all domains. You take any domain and you can see big data problems. Let's talk about science first. The Large Hadron Collider at CERN produces about 1 petabyte of data every second. That is right, 1 petabyte every second. Mostly sensor data from their equipments. Their volume is so huge they don't even retain or store all the data they produce. NASA gathers about 1.73 gigabytes of data every hour about weather, geolocation data from their satellites, etc. Let's talk about the government. NSA, that is National Security Agency, is known for its controversial data collection programs. And guess how much NSA's data center at Utah can house in terms of volume? A yottabyte of data. That is 1 trillion terabytes of data. Pretty massive, isn't it? In March 2012, Obama's administration announced about $200 million in big data initiatives. So you can understand the significance behind big data and its analysis. Even though we cannot technically classify the next one under a government, it's an interesting use case, so I included it anyway. Obama's second-term election campaign used big data analytics, which gave them a competitive edge to actually win the election. That's pretty powerful, isn't it? Next, let's talk about the private sector. With the advent of social media like Facebook, Twitter, LinkedIn, etc., there is no scarcity of data. eBay is known to have a 40 petabyte cluster and Facebook a 30 petabyte cluster. These numbers are probably much more now since the stats are a little old. Big data is not only produced and analyzed in social media companies, but also in retail space. It is most common in several major retail websites to capture clickstream data. For example, let's say you shop at Amazon.com. Amazon is not only capturing data when you click checkout. Your every click on their website is tracked to bring a personalized shopping experience. When Amazon shows you recommendations, big data analytics is at work behind the scenes. I've included the sources for all the information I provided in this slide in the lesson notes. Now you should be convinced that big data exists, even if you did not believe it before. So, we have big data. So what? Big data comes with big problems. Let's talk about few problems you may run into. Since the data sets are huge, you need to find a way to store them as efficient as possible. I'm not just talking about efficiency in terms of storage space, but also efficiency in storing the dataset that is suitable for computation. Another problem you should worry about when you deal with big data set is about data loss due to corruption in data or due to hardware failure. And you need to have proper recovery strategies in place. The main purpose of storing data is to analyze them, right? How much time does it take to analyze and provide a solution to a problem using your big data is a $1,000,000 question. What's good in storing the data when you cannot analyze or process the data in reasonable time? With big data sets, computation with reasonable execution times is a challenge. Finally, the cost and the most important challenge. You're going to need a lot of storage space and a lot of computational power. So your solution that you plan to use should be cost effective. But what is the need for new big data solution like Hadoop? Why traditional database solutions like MySQL or Oracle is not a good solution? With traditional RDBMS, you will see scalability issues when you start moving up in data volume in terms of terabytes. You'll be forced to denormalize and pre-aggregate the data for faster query execution time. And as the data gets bigger, you'll be forced to make changes to the process in terms of changing the indexes, optimizing the queries, etc. If you worked with databases before, this will sound very familiar to you. Assuming your database is running with enough hardware resources, when you see a performance issue, still you have to make changes to the query itself or the way in which your data is accessed. There is no working around it. You cannot add more hardware resources or more computer nodes and distribute the problem to bring the computation time down. Meaning to say, database is not horizontally scalable. You cannot add more resources or more computation nodes and hope the execution time or the performance will improve. The second problem is databases are designed to process structured data. That is, when your data does not have a proper structure, in that case, a database will struggle. Furthermore, a database is not a good choice when you have variety of data. That is, data in several formats like text, images, videos, etc. Other challenge is a good enterprise-grade database solution can be quite expensive for relatively low volume of data. When you add hardware costs and platinum-grade storage costs, it's going to be quite expensive. Next, distributed computation solutions like grid computing are essentially many nodes operating on data parallelly and hence does faster computation. But there are two challenges though. The first one is grid or high performance computing is good for compute intensive tasks with relatively low volume of data, but does not perform well when the data volume is huge. The second problem is grid computing requires a good experience with low level programming to implement, and hence it is not suitable for mainstream. So a good solution should, of course, handle huge volume of data. It should provide efficient storage, that is, ability to store data efficiently. Data loss is unavoidable. So the proposed solution should implement good recovery strategies. And the solution should be horizontally scalable as your data grows. Most importantly, it should be cost effective. And finally, minimize the learning curve. It should be easy for programmers and data analysts and non-programmers to work with the framework or the system. This is exactly what Hadoop offers. It can handle huge volume of data. It can store data efficiently in terms of both storage and computation. It has good recovery solution for data loss in place. It can horizontally scale, and that is very important. So as your data gets bigger, you can add more nodes and everything will work seamlessly. It's that simple. It is cost effective, meaning we don't need any specialized hardware to run Hadoop. And hence, it's great even for startups. Finally, it's easy to learn and implement. So, is Hadoop a replacement for database? The straight answer is no. There are things Hadoop is good at and there are things that database is good at. Look at this slide. RDBMS work exceptionally well with volume in low terabytes, whereas with Hadoop, the volume we speak is in terms of petabytes. Hadoop can work with dynamic schema and can support files with many different formats, whereas in database, the schema is very strict and not so flexible and cannot handle multiple formats. Next important distinction is scaling. Database solutions can scale vertically, meaning you can add more resources to the existing solution. And to make any improvements, you have to improve the process itself, like tuning the queries, adding more indexes, etc. But it will not scale horizontally. That is, you cannot bring down the execution time, or you cannot improve performance of a query by simply adding more computers. That is, you cannot distribute the problem into many nodes. Finally, the cost. Your database solution can get expensive very quickly when you increase the volume of data you're trying to process, whereas Hadoop offers a cost-effective solution. Hadoop infrastructure is made up of commodity computers, meaning there is no need for specialized hardware. Commodity computers doesn't mean cheap computers. It is still enterprise-grade hardware, but relatively inexpensive as opposed to specialized equipment. It is important to know Hadoop is a batch processing system. It is not as interactive as a database. You cannot expect millisecond response times with Hadoop as you would expect in a database. With Hadoop, you write the file or dataset once and operate or analyze the data multiple times. Whereas with the database, you can read and write multiple times. But the gaps between Hadoop and RDBMS are closing in. Hadoop offers a cost-effective solution to big data problems. But Hadoop is not the only solution that is available in the market now. NoSQL databases like HBase and Cassandra bring a great deal of value in analyzing huge volume of data. And it's a great alternative for RDBMS. When I say huge volume of data, we are talking millions of columns. That's right, millions of columns and billions of rows. At this point, you should have a good idea of what is classified big data and what are the challenges with it. We also saw some of the offerings of Hadoop in comparison with traditional systems. In the Understanding Big Data Problem lesson, we'll dive deeper into how Hadoop actually proposed solutions to the big data problems that we discussed in this lesson. With that, let's wrap this lesson. See you in the next lesson.